Welcome back. So in this lecture, we want to talk very briefly about another type of deep learning architectures, and that's recurrent neural networks. So far, we basically discussed the connection between empirical risk minimization and maximum likelihood estimation. So what we said was that in the context of, for instance, classification and regression, our training task, basically finding a model that minimizes the average loss over the training data, is equivalent to maximizing the likelihood of the data. Okay. Now, we discussed this in the context of classification and regression, meaning that I have a pairs of, let's say, x and y's, where x are features and y's are labels. Okay. But in many applications, we are dealing with sequences. Okay. So let's say I have observation at time 1, observation at time 2, at time 3, etc. And the goal is to, let's say, given a set of observation, predict what the next observation would be. Okay, and this is very frequent in practice. For instance, in scenarios where we work with financial data, in language modeling, and also like when you work with a sequence of nucleotides, basically DNA data. Okay, so how can we approach utilizing deep learning models for these kind of problems? Okay. So one natural idea is to assume that there is a causal model, okay, that dictates the relationship between these observations, meaning that the next observation only depends on all, let's say, all the previous observations, okay? So xt only depends on all observations from time 1 to time t minus 1, okay? So in particular, we can imagine that for any time t, xt, let's say the function could be a highly nonlinear function of all the previous observation, where our function is parametric. So it depends on some parameter w star. Okay, so so you see hopefully where I'm going. Let's say that a is some, I don't know, MLP or something like that. It has certain parameter. If we have access to let's say like a data set of these time series, maybe we can leverage like a training algorithm to minimize the empirical risk, or a problem similar to that. Find this W star. Therefore, for any time, we'll be able to make a good prediction of what the next observation would be. Okay? This approach is actually referred to as the autoregressive models. Okay. Now, how can we basically again make a progress here? So the idea is that we want to utilize parameterized functions to represent this, let's say, highly nonlinear relationship. Okay, so and therefore we'll be able to follow a similar maximum likelihood approach that we talked about before to find the optimal parameter. So in some sense, we want to find the optimal parameter that maximizes the likelihood of the next observation. Okay, now a simple example here is that instead of a highly nonlinear A with parameter W star, we just consider a linear relationship. Okay, so in particular, the observation at time t plus 1 is some, let's say, parameter scalar times the observation at time 1, another scalar at time 2, so on and so forth, and another scalar at time t. Right. So these ways, for instance, could indicate the importance of the observations we've made so far in terms of what the next observation would be, right? So for instance, if all of these weights are 0 except the last one, we could say that we have something like a Markov model, right? So that the given the present, future is independent of the past, okay? So this is a model that we can adopt, and basically, if you have access to certain data of sequences, we'll be able to find these, let's say, these ways. But there is an issue here, and the issue is that we're going to have too many features, especially as time grows, because we are sort of imposing the following requirement that every like the next observation depends on every single observations we've made so far, right? So it depends on x1 through xt, okay? So therefore, if I have a very, very long sequence and I want to make a prediction on what the next x would be, I may have to deal with like billions of weights here. Like, so I may have to again consider contribution of billions of features. Okay. So how can we sort of deal with this issue? A simple solution is to limit the dependency of x. Okay, so it's very natural. So we consider a window, right? So of size tau, and we say that every observation depends only on the past tau observations. Okay, and tau, let's say, is a constant that does not grow with time. Okay. More generally, what we want to do is therefore to find a latent variable that effectively summarizes dependencies of the observation. Okay, such that if we know this latent variable, we can make a good next prediction without imposing explicit dependency among all observations. Okay, so basically, a little bit more mathematically, what we want to do is the following: we say that let's say xt for any time is a let's say a nonlinear function of with some parameter w star and a latent variable ht. So you can think of it as history. Okay, so something that summarizes the history of what's been going on so far. And the history itself depends, let's say, using another nonlinear function with parameter omega star on the previous history and the new observation that I'm making. Okay. Now, for instance, in the example that I mentioned here, h. So for this example, our history is basically this window of size tau of observations. Okay. And to update the history, we throw out the last observation and replace it with the most recent one. Okay, so that's how we would update the history. And in this case, for instance, we can still follow the linear model that we talked about before, right? So basically, let's say we have a set of weights that we want to learn them. So in that case, the number of weights that we have to learn is only tau. Okay, so that's the size of the history, and that doesn't grow with time. So therefore, we have sort of reduced the number of learnable parameters drastically from order of let's say t to a constant number. Okay. Now, more generally, we can go beyond a linear model and represent these functions with neural networks. Okay, and learn the parameters by fitting the data. Okay, so in particular, we can, let's say, build the neural networks and show how the information sort of propagates. Okay, so in particular, this figure is meant to represent this mathematical equation, right? So in particular, we get as input our observations. Let's say we get an observation at time t minus 2. We use that to get history t minus 1, and based on the history, we're going to make a prediction. Let's say we feed it to our model A. So here we feed it to our model G. Okay, so we feed it to model A, we make a prediction. Now, to update the history, we're gonna make another observation, use the previous history, okay, and then we're going to update the history, use that to make another prediction, and then we continue following this process, make an observation, update the history, make a prediction. Okay, so that's basically the idea of latent modeling in autoregressive models. All right. So as we talked about, we want to sort of utilize neural networks to represent those parametric functions. Okay, and what we can do, a simple idea is to use multi-layer perceptrons that we've talked about before. Okay, so remember, a multi-layer perceptron can be represented as follows, right? The activation or the output of a layer is basically the weight of the layer times the previous activation or the output of the previous layer plus some bias, and then we feed that into a nonlinearity, basically an activation function such as ReLU, tanh, or sigmoid. Okay, so and we may have, like, let's say L layers, And what's our first input, our first activity? That's basically the input, let's say X. Okay. So for latent autoregressive modeling, basically this is what we want to do. We want to find a way to update the history, and we're going to use an MLP to represent this nonlinear function G. Okay. So what we do then, we're going to basically say that the next history is some nonlinearity, some activation applied on the following. We have, let's say, a learnable parameter W times the previous history plus some bias plus another learnable parameter times our input signal xt. Okay. So essentially what we are doing here is that we are concatenating. So let's say we have this big matrix W, and we are multiplying that with the concatenation of the history at time t minus 1 and X. Okay. So, and then we add some bias to it. So this is exactly the MLP operation we had before, right? So, but in that context, we didn't have like this history. We would just multiply this weight matrix to the input, which is basically the output of the previous layer. Okay. Now this is basically called a recurrent neural network, and we have only one hidden layer, okay? Because we feed the X, the input, directly into, let's say, this nonlinearity, let's say the sigmoid, and then we, based on that, we're going to make a prediction, okay? What are the learnable parameters? As I mentioned, the learnable parameters are the weights that we use to multiply with the history, the previous history, weights of the input X, and the bias, okay? But one crucial thing to note here is that the parameterization cost does not grow with the number of time steps, okay? So it doesn't matter if I have a sequence, if I'm handling a sequence of lengths 1,000, 1 million, 1 billion, the number of parameters I have to learn is always the same. It's always W, W tilde, and B, okay? So it's not growing with time, okay? So this is very similar to that like setting up a window idea we discussed in the previous slide, okay? Now, this figure is could be helpful to see how the information flows. So we have, let's say, our inputs, okay? So these are the observations. We take them, let's say, and then we concatenate them with the history. We feed them, let's say, through some nonlinearity, some activation function, and then based on that, we're gonna make a prediction. So basically, we're gonna generate an output. We use the history, a new observation, and feed that into an activation to update the history, and then make another prediction, and we continue this process for all time steps. Okay. All right. So that's basically recurrent neural network is a very useful family of neural networks that is designed to deal with scenarios where the data is actually a time series data. Okay. And there have been lots of improvements to the simple recurrent neural network that we talked about in the previous slide. And I'm not going to go over the details. I'm just listing them for your information. So for instance, long short-term memory neural networks and gated recurrent unit, GRU, are designed to deal with the fact that the simple RNN we talked about may suffer from information loss, especially when we deal with very long sequences that contain very long-term dependencies. Okay, and the solutions that these new architectures are employing, I would say, in nature are sort of similar to this skip or residual connection that we talked about in our lecture on CNNs. Okay. So that's one idea. So basically, design like some connections or like and complicated architectures to make sure we can still learn long-term dependencies. Another idea is to increase the learning capability by having more layers of RNNs. So in the previous slide, what we saw was basically an RNN with a single hidden layer. We can have multiple hidden layers. Okay, so as I'm showing on this figure on the left-hand side. So we take the input, we feed it, or to learn, let's say, the history or the latent parameter of the first layer. We use that to learn the latent parameter of the second layer, and so on and so forth for the LS layer, and then we make a prediction. Okay, so that's the idea of stacking RNNs to have multiple hidden layers as opposed to one. Okay. Another thing we can do to basically make sure that our model is more effective in terms of capturing dependencies in the sequence is to not only process the data, let's say, from left to right in a causal manner, but also from right to left. Okay, and this is basically called bidirectional RNNs or bidirectional LSTM if you are using an LSTM model as opposed to an RNN. So here's a simple way to demonstrate how this works. Okay, so previously we were basically using the observation, let's say x1, to update the history and then make a prediction for time 1. Okay, and we would go in this direction. So we would use h1, the new observation, to update the history and then make a prediction. So that was our previous architecture. In the bidirectional approach, we also process data from this direction. Okay, so we take let's say the last one, use that to get this history, make a prediction. Okay, and then we're moving in this direction to update this new set of, let's say, latent variables and update them. One issue of the RNNs and also the CNN is that they need to work with data of a predefined size. So if I change the size of the dimension of the image, the architecture is not gonna work. Or we need to like go through a lot of sort of problems to basically make sure that our architecture can work with data of a different dimension. Okay. For RNNs, there's also another issue that so the implication for RNNs is therefore that the sequence length typically needs to be fixed such that we can utilize the RNN. And if you change the length of the sequence, we have to go through a lot to make sure that our RNN is applicable. Okay? And this could limit the applicability of the recurrent neural network architectures that we've introduced. Okay? In addition to this issue, RNNs also suffer from another issue, and that's sequential computation. Okay, so and this is not ideal because there has been a lot of advances in hardware to leverage parallel computation, right? So and therefore RNNs cannot leverage the parallel computations, let's say in GPU, to accelerate the training and also the inference process. So therefore, there has been a breakthrough in the literature to design a new kind of architectures that's called transformers, which leverage, I would say, two important mechanisms. The first mechanism is the attention mechanism that I'm going to very briefly talk about that, and another one is positional encoding, right? So essentially, you want to leverage an encoding procedure to know which, let's say, what's the location of, let's say, a word in a specific sequence, right? So basically, and a sentence is basically a sequence, right? So we use this positional encoding to remember what was the location of each word, and therefore we should be able to sequence the data, to process the data not only in a sequential manner, but in fact in a parallel manner. Okay. And the idea is that, again, leveraging these two ideas, we can alleviate both of these issues. So we can deal with sequence of varying lengths, and also we can work with parallel computation. But the catch is that we're gonna incur higher computational costs. Okay. All right. So what's the attention mechanism? Let's talk about it very intuitively and very simply. So I would say it is useful to think of it as a database, right? So databases are basically a collection of keys and values, okay? And let's say that you want to interact with a database, okay? So what you're going to do, you're going to, let's say, make a query, queue. And it doesn't, you can always make a query, okay, regardless of the size of the data set, right? So let's say that you have a your query is basically a specific key. So you give that key to the database, and the database is going to return the corresponding value. Okay. So and it doesn't matter what's the size of the database, how many pairs of keys and values you have in the database. Okay. And the attention mechanism, I would say, leverages the same idea, but instead of returning one value, it basically returns a convex combination of all values in the data. And so it's basically a weighted sum. And the weights are designed such that they are larger if there is a higher correlation between the query that you're making and the key in the database. Okay. So therefore, the attention mechanism is as follows, right? So let's say you have a database, okay, and you are making a query, okay. So in the simple case, based on your query, only a single value would be returned. But in this case, we are returning again a weighted combination of all values in the data set. And here I'm using M to denote the size of the database. Okay. So what are these weights? These weights are basically, again, dependent on how similar the query and the keys in the dataset are. The larger the similarity, the higher these weights. Okay. So in particular, we're going to use this expression. Okay. So we do some normalization to make sure that these weights are non-negative and they sum to 1. So basically, we want to have a convex combination. Okay. And you know that in this expression here, in the numerator and the exponent of this exponential function, I have the inner product between the query and the key, right? And inner product is basically nothing but a notion of correlation, right? So the more aligned key and query are, the larger the inner product, right? Therefore, the larger the weights. Okay. So this normalization, I hope you recognize that this normalization is basically the softmax normalization that we talked about before in the context of softmax classification. There we also basically wanted to make sure that our output is basically like a probability vector. So therefore we are utilizing the softmax to ensure both non-negativity and the fact that they sum to 1, the probability sum to 1. Okay. So this is basically the attention mechanism, and it is used in the transformer architecture. So in practice, this query value and keys, they are basically matrices, and they also have some learnable parameters that we're going to learn from data. Okay. And here is a figure again demonstrating the attention mechanism. So let's say you have a certain query and a number of keys. So these are fed to the attention mechanism, right? So let's say you've learned the weights, and then for each corresponding key query pair, you're going to receive a value, okay? And then you combine them to make an output. So this is a short overview of the third type of architectures, basically recurrent neural architectures. In the next lecture, we're going to talk about some learning techniques or training techniques that we use to train deep learning architectures. I'll see you next time.